start. Welcome everybody to this new AJS. Today it's been a pleasure to introduce you this new speaker, Luca Guastoni. He's a postdoc at the University of the Technical University of Munich, Germany. And today's talk will cover deep reinforcement learning strategies, and its title is Deep Reinforcement Learning and its Application for the Control of Wall-Bounded Turbulent Flows. So, Luca, you can start if you want.
Right. Thank you very much for the invitation and for the possibility to talk. I hope you can hear me well. If you have any question, I think it's good. You can write it in the chat or anything. I'll keep an eye on it so that maybe we can also tackle them while we are talking. So the outline of, as Guglielmo, I think it was, suggested the title for today is Deep Reinforcement Learning and its Application for the Control of Wall-Bounded Turbulent Flows. And today's agendas looks more or less like this. So first, I don't know what is the background of the people listening. So I will give an introduction to reinforcement learning and to its fundamentals so that we are all on the same page to start. And then I will show up two applications of deep reinforcement learning in turbulent flows, namely for drag reduction and for coherent structure manipulation. And finally, I want to touch upon another topic, which has been a little bit the work that I've been doing here in Munich recently, that is regarding the optimization challenges that are present in reinforcement learning. And then we go to some conclusion and outlook for the next research. So first off, reinforcement learning. Reinforcement learning is a mathematical framework to solve Markov decision processes. It was introduced by Sutton in 1988. And the idea is that we want to solve the problem with this framework. We need to identify the following elements in our problem. First off, we have our controller or agent, which essentially is the controller, while every other element in the problem is modeled within the environment, which is characterized by a state variable S. Now, the agent perform an action called A on the environment, and it will, so that the environment will evolve to a successive state st+1, and is gonna, according to a predefined transition function, and then it will also return to the agent a certain reward. Overall, the idea is that the goal is to define a policy that, given the current state, provides us the action to perform so that we maximize the overall reward. So more in practice, what we do is that we have a starting state that is sampled from an initial distribution. And then once we have chosen the action to perform based on the state and the action that we currently have, we're gonna transition to a different state and gather the corresponding reward. Overall, the idea is that we are gonna interact with the environment and gather these, let's say, tuples that are given by the state, the action, and the reward at this time step, and also the state that we are landing on after performing the action. And overall, this set of transition, we're gonna call them trajectory, or sometimes, depending on the situation, also an episode. Overall, our goal is to maximize the discounted reward over the entire trajectory, and to define a policy that, given the state, provides us the action to perform, so that, in general, we are able to maximize these expected return over the entire trajectory. Now, there are a couple of more important functions that we're gonna introduce that are called state value function and state action value function, which essentially are the expectation of these expected return, but while conditioned on the initial state or on the initial state and initial action. Here, the main difference is that this initial action A may not be taken from the current policy according we are operating. And essentially, the idea here is that this function can give us the opportunity to assess what is the let's say the let's say, the quality of a specific state or a specific state and action pair. The biggest issue here is that we need to approximate this function because whenever we, for instance, we take into account this Q function, which is the state action value function, if we are able to identify the optimal policy, this optimal policy will be the one that will maximize the expected reward on a specific trajectory. And by knowing this function, we are also immediately able to identify what is the policy. So, and in practice, what is the action that we need to perform in each state in order to, get the maximum reward. One of the issues that we need to tackle here is the fact that the value at each state is not known a priori. And this is something that I'm gonna come back later after the DRL application in turbulent flows, because it's something very important and fundamental that we still struggle in some sense to understand and to perform. Because what we do to evaluate the value of each state is to use reinforcement learning, and which is essentially a trial and error procedure. So we perform an exploration of the different state and action in order to try to learn and visit as many states as possible in order to understand what are the best combination of state and actions. And here, at this point, you can see that there are two conflicting targets or objectives that we have. In fact, on one end, we want to explore as much as possible the actions and the states that are available in our system. But at the same time, our goal, if you remember from the previous slide, was to maximize the reward. So, which is usually identifying using the word exploitation. So essentially, during the exploration phase, during the reinforcement learning, we want to balance these two elements, because if we are not seeing all the states, then what is happening is that we are only focusing on a specific set of states without the guarantee that these are going to be actually the best combination of states. And while if we try to exploit too much, we are not seeing other alternatives that we have seen. One common example is that imagine you are on campus and you have different options to eat food, and then if you find out that there is one specific restaurant that you really like, if you want to maximize the reward, what you're gonna do is that you're gonna continue eat at that restaurant without never trying anything else. However, this doesn't give you the certainty that there is not a better restaurant that you will like more eventually. On the other hand, if you try to explore all the different restaurants, you want to also try to explore the different restaurants in order to see whether there are better options or worse options, and try to categorize them. So, of course, this exploration can be quite costly. And if you imagine that the policy is providing essentially a mapping from the state space to the action space, then these two spaces could be, in principle, also infinite dimensional. So this can be really hard to explore in a very efficient way, in a very complete way. So oftentimes what we do is that we approximate these quantities by means of neural networks in particular, but we will see that any function approximator can actually be used in this situation. So reinforcement learning essentially is part of a bigger family of machine learning, and sits a little bit in between supervised learning and unsupervised learning, while not being any of them. Because on supervised learning, what we have is that we have a specific target for our model to let's say get close to, whereas in unsupervised learning, our goal is to try to discover what is the structure, the hidden structure of the data that we have at our disposal in an automatic fashion. While reinforcement learning also has in part to so to speak get a sense of the data that is getting as input, at the same time is not in general, this is not in general sufficient for to be able to learn a control policy. control policy in practice. Within reinforcement learning, we have two different big families of algorithms that are called model-based reinforcement learning and model-free reinforcement learning. In case of model-based reinforcement learning, what happens is that we have a model of the environment, and we typically use it also to perform some form of planning. So we decide what action we are going to perform for a long horizon in the future, because we use our model of the environment to kind of predict how the environment is going to evolve based on our actions. But what has been mostly popular for the time being is model-free reinforcement learning, in which we don't assume any kind of model for the environment, and we just learn from the interaction. In general, model-based reinforcement learning is more efficient from the data perspective, but at the same time, there are pitfalls in the moment that we try to deploy the algorithm in the actual environment, because typically what happens is that the reinforcement learning could be able to exploit some limitation of our model, so that we're able to actually control let's say, our model of the environment. However, whenever we move to the actual environment, typically these limitations, these let's say shortcuts, are not available, and so the performance in the real world or in the real environment usually is much worse than what happens in general. So in model-free, this is not a problem, and typically we have two different approaches based on the quantity that we are trying to learn. On one side, we have value-based methods, which are trying to learn these state value function or the state action value function that we were discussing before, or alternatively, we are trying to learn directly the policies, so a mapping from the state space to the action space, and that's the case of policy-based methods. Third category, which is sort of in between, is what we call actor-critic methods. And actor-critic methods consider two different, in this specific case, neural network models. And one is the actor, which is going to learn the policy, and the other one is the critic that is going to learn instead the value function. So we can definitely mix the two. And that's in general the category from which we're going to take the algorithms that we're going to be used in our applications. So speaking of applications, I want to have a small introduction. What is the motivation behind using DRL in turbulence control? So of course, our goal is to manipulate the physical characteristics of the flow. And this is something that we have been trying to do since forever, essentially. And in fact, in one of the many reviews that you can find online on flow control, you find that the fletching of arrows are actually one of the first and earliest attempt of flow control, in which we have been adding these feathers to arrows in order to try to make them fly further. So that's a very early attempt to do this. And this is categorized as a passive control strategy, since while on the other side, we can also have active ones whenever we are introducing some kind of energy, some sort of energy, in order to actuate and perform this control strategy. Now, turbulent flows are very interesting because on one hand, we have been trying to, let's say, work on fluid flows in turbulence for a very long time, but still today there is a large number of studies that are published on this topic every year. And this depends on the fact that turbulence is a very high-dimensional and very non-linear phenomenon that it becomes a little bit tricky to control using traditional control frameworks. The thing is that whenever we want to design a control strategy, not only we need to decide which phenomenon we want to control, but also we need to design and place the sensor in order to measure the flow properties, and also the actuators in order to modify these properties. And in this sense, in this regard, reinforcement learning provides an interesting approach, because it provides an end-to-end algorithm that in principle is able to help us devising new and possibly more effective control strategies. So Our application and for reinforcement learning, for deep reinforcement learning case, is the flow into a 3D turbulent flow, into 3D turbulent channel flow, sorry, and which is a good model for many different wall-bounded flows. And in particular, what is interesting for us is that this case has been studied for about 30 years by now in with simulations. And so we have a number of different baselines that we can compare to whenever we are designing our own policy. We are going to consider two different domain sizes, which are minimal channel and larger channel, and both at Reynolds number RETA 180. We're going to consider the minimal channel first because this is going to allow us to iterate in our simulation while staying computationally cheap, whereas then we are be able to transfer those policies on a larger domain. In this case, in particular, we are going to consider an open channel flow, which means that it has only one wall at the bottom and then a symmetry condition on the top. However, because essentially this allows us to better isolate the features that are related to a single wall in a turbulent flow. However, it should be noted that other groups relatively recently or contemporary to our work have been testing this same approach for a fully regular channel, a standard channel with both walls on the top and on the bottom. So first off, we're going to describe what is our baseline. Baseline is introduced in 1994 and it's called opposition control. Opposition control is a form of reactive control. And what we do here is that we sense the flow at the given distance from the wall in this plane, and we are measuring the fluctuations, the wall normal fluctuations at this location, and we are actuating with blowing and suction at the wall in order to sort of counteract the effect of the fluctuations at that level. In our case, what we are doing is that we are trying to mimic the settings somehow of these opposition controls so they can better compare with them. So our observed state for the RL environment is going to be the streamwise and wall normal component of the velocity at the given wall normal location. The reward is going to be the wall shear stress, which means essentially, which is a proxy for the drag that we can have in the flow. And finally, the control will be in the same way performed using a wall normal velocity distribution that is imposed at the wall, so which is mimicking what is a blowing and suction control. Now, this is, of course, the setting, but despite this first presentation, there are several methods, several ways in which we can actually implement this control in practice. So the first and maybe naive approach that we can have is that we can use a single agent for the entire environment. So in this case, assuming that our simulation has dimension nx and nz in the streamwise and spanwise direction, respectively, we're gonna have a state that has the size because we are sampling the velocity at the plane in all the points, and the reward is gonna be computed on the entire domain, on the entire let's say lower wall of the domain, and also the control is gonna be defined in each and every point of the domain at the wall. Now, this approach is, of course, has the benefit and the advantage of being relatively simple in terms of implementation, which means that is relatively straightforward. However, it has two strong drawbacks. Well, the first one is that we have relatively large action space, which means that whenever we are designing our controller and our agent, we're going to need to explore all the different combination of actions that are possible in this environment, and this makes it quite difficult to explore in let's say in an efficient way, because there are a number of different combinations that are very similar but might have very different effect on the flow. So it's not efficient from the computational perspective, but most importantly, there are few missing physical properties that we want to enforce within our simulation. And so these properties are in particular locality and transitional equivariance. So locality is given by the fact that we are considering a turbulent flow in which what is happening in a certain part of the domain very quickly decorrelates how the signal of the velocity, let's say, quickly decorrelates when we move farther away in space from the point where we are measuring. So it's very unlikely that knowing the velocity far away from the point of actuation will actually provide some sort of indication to what is the best action to perform. And at the same time, we also have the transitional equivariance. Transitional equivariance is important in this particular case because, well, in this case, we have periodic boundary conditions. So, of course, we let's say the simulation could be translated without problem. But the main important thing is even if there was not this translational invariance, is that if you have a specific feature of the flow that you are able to control and you control in a certain way in a certain point of the domain, there is no particular reason why this other feature in the homogeneous direction is going to be, the actuation strategy will not be different in any other point of the domain. So it is important to try to enforce these physical properties in order to maximize also the computational performance. This is something that we didn't come up with in first place, but it's something that we mutuated from this other work from Belus et al., in which they were trying to control a one-dimensional unstable falling liquid film. So in this specific case, the idea or what they wanted to achieve is actually that they wanted to delay the onset of chaotic development of the flow film. And to do this, they were introducing an actuator, and the actuator was measuring the state just before the actuation point, and the reward was calculated just afterwards. Of course, a single actuator is not enough to control the entire simulation. So in practice, what we need to do is that we need to add maybe a second actuators and then a third actuators or n actuators in general. And these actuators, in principle, have no reason to be different one from each other. So what we're going to do is that we're going to consider one single policy for each and every of these agents. So we are able to use all the, let's say, transitions that we have seen at the very beginning from each and every actuators in order to learn a common policy for all of them. And this approach is not anymore what we call a single agent reinforcement learning, but then it becomes a multi-agent reinforcement learning. So now if we go and revisit our simulation and our turbulent flow simulation in 3D, what we're going to do is that instead of having a single agent, we're going to have a grid of agents in X and Z, so that we're going to have that will all share the same policy, and that will try to learn a local and translational invariance one. In this particular case, we are considering the number of control agents that is equivalent to the number of points that we have in our simulation. But of course, in principle, there is no limitation to the fact that an agent could also be responsible or control different points at the same time. So in this case, what happens is that we have the observed state that now is not anymore the one on the entire domain, but rather only on a limited portion of it. The reward is now anyway computed on the entire flow, flow domain, not because, it's mostly because for two reasons. One is computational, because averaging on a larger surface is going to give us a less noisy signal, but at the same time, we don't want the agent to learn how to reduce the drag only on the limited area that we are interested in, but rather try to have them work all together in order to reduce the overall drag in the flow domain and the flow simulation at one point. At the same time, the control is not going to be on the entire domain, but rather only on the points that the agent is responsible for. Now, just a couple of notes on how this was implemented. We have an actuation interval. So at regular times, there is an actuation. This actuation time was tuned based on the, let's say, on the opposition control, our baseline that we use, so that kind of maximize the effects of the opposition control, so that we have a somewhat fair comparison. And also, whenever we agree on, or our agent provides a new value for the control, what we do is that we move linearly from the old value to the new one within between the two actuations, in order to avoid numerical instabilities related to the fact that we are changing the boundary conditions in a very short time, in a very short number of steps. We are considering only a limited actuation intensity, and this is designed in order to try to force the agent to learn an energy efficient policy. And as I mentioned before, all the actuators are going to use the same policy, so we have shared weights among different agents. We're going to consider, to learn the policy, we're going to use a deep deterministic policy gradient, and we're going to not update each and every action our policy, but rather every 10 of them. And in particular, we are going to perform 100 actuations per episode, and then we're going to restart the simulation from the initial condition that we decided before. So first case that we're going to have a look at is the minimal channel, which are, let's say, the first results we're going to have a look at. And here we have a smaller domain, and which is computationally efficient, as I was mentioning. And the important thing to remember is that deep reinforcement learning is a trial and error process. And for these, we had to test our, let's say, algorithm on both different initial conditions that are considered for learning, and also we perform different runs for each and every initial condition. As you can see from here, there is clearly a difference in the different runs, because in each and every run, we are not performing the same control, and there is also a certain degree of exploration that is enforced in the algorithm. So each and every run becomes rapidly decorrelated from the other and providing different outcomes in these cases. And you can also see that sometimes it just fails. So sometimes it works, sometimes it just doesn't. And so it's very important to run several runs even with the same conditions, because it being a trial and error problem, trial and error algorithm, is very difficult to try to reproduce exactly the same behavior, especially with an environment which is also highly chaotic and has the turbulent flows, essentially. So after we have learned the policy, what we're going to do is that we're going to test them in order, without exploration this time, in order to make sure that our results are actually performing well. Our policy is actually performing well. And from the results here, you can see that drag reduction can actually be achieved. And in particular, with certain, despite the certain sensitivity with initial condition, we can see that on average, we are able to outperform what is the baseline, which was opposition control, regardless of the initial condition. What is interesting for us here is that opposition control at the beginning normally would provide a 26% drag reduction, whereas with our DDPG policy, we're able to achieve up to 43% drag reduction. Looking beyond a little bit what was the mere value of the drag reduction, we wanted to see what the policy was actually doing in our simulation, how it was affecting the simulation. So what we had a look at was quadrant analysis, which is a plot that shows how they are the joint probability distribution of the streamwise and wall normal fluctuations. Here you can see that normally, if we have no control, the flow is dominated by sweep and ejections, and in particular, ejection are the one with positive. Here in Q2 are the positive wall normal fluctuations, and and negative streamwise fluctuation, and also sweeps, which are instead the one with positive streamwise fluctuation and negative wall fluctuation. Whenever we apply opposition control, what happens is that we reduce the range of fluctuations that we have. However, the overall structure of the flow and overall structure of this joint probability distribution is not really altered. On the other hand, whenever we are applying our DRL policy, we have definitely a stronger impact on the fluctuation distribution that you can observe here, with the stronger fluctuation in the wall normal direction, whereas a much smaller fluctuation in the streamwise direction. Now, we mentioned at the beginning, or in the middle actually, that our learn policy, it is local, which means that it actually can be applied without retraining and without any change also to other flow cases. And for this reason, we wanted to apply also it to a larger channel, so in which we have a more comprehensive range of turbulent structure that needs to be controlled. It should be noted here that we have a different resolution in the larger channel, which means that we also have a different number of agents that are working on the control of the flow. So if we perform the same analysis that we did before, we see that on average, our DDPG is performing slightly worse than what was happening before, because right now DDPG is only providing 30% drag reduction. However, it is, let's say, averaged on the different initial condition. However, we are still performing much better than original opposition control, which is now at 20%. Now, we could argue that now the DDPG is performing worse, mostly because in this larger domain, for instance, we are able to simulate different larger number of turbulent structure and larger number of streaks, for instance, and the interaction between the different streaks is something that we are not able to simulate in the minimal channel, and for this, our reinforcement learning agent never saw this interaction and is not able to either take advantage or, let's say, deal with them in general. So that's something that without retraining in a larger channel, then we are not really able to, let's say, to control actively. At the same time, if we look again at the quadrant analysis, what we can see is that essentially we have more or less the same situation that we saw before, just more refined because we have a larger number of samples in this case. So summarizing this part boils down to say that we are actually able, and was a first, let's say, occurrence of these, we are able to learn a drag reduction policy in using multi-agent reinforcement learning in turbulent flows. And most importantly, our policy is able to outperform existing baseline, in particular opposition control, both in the minimal channel and in the large channel. And also what is interesting, in my opinion, is also the fact that the DRL policy is modifying the let's say the flow physics or manipulating the flow physics in a profound way. So it's not just gonna imitating what we didn't just rediscover existing control policy, but rather we discover new ones. And of course, we tested all these only on a relatively small Reynolds number, which was rate tau 180. However, recent works, which are not cited here, but they have been started looking into higher Reynolds number, have shown that this approach could also help us learning something in those situations. But most importantly, what is missing for us is also trying to have a further insight on the control strategies. And in particular, this later observation is the one that motivates the next part of this talk, which is trying to answer the question whether we can actually use deep reinforcement learning as a scientific discovery tool. So as we said, multi-agent DRL can be used to design new control strategies, but now we want to see whether we can explore scientific hypotheses using these automated tools. And here there are a couple of motivating examples that I want to bring up. The first one was from Jimenez in 2018, in which he used unsupervised learning to try to identify what are the significant turbulent structure in decaying isotropic turbulence. In this case, it was a 2D problem. And another case used instead supervised learning and explainable AI techniques in order to identify what are the coherent structure in wall-bounded flows that are interacting let's say, and not all the structure, but trying to identify the most important structure from the energetic point of view. So in the same spirit, we try to do something similar using also reinforcement learning. And in particular, our attention is devoted to turbulent structures and drag reduction. So from physics, we know that the region close to the wall is responsible for the highest rate of turbulent energy production. So the anisotropy close to the wall is what makes the flow actually turbulent in this case. And in particular, there is a regeneration cycle of the turbulent structure that can be identified and has been described back in 1999. And one of the most important structure that we have to consider in this situation are low-speed streaks, and one of them is depicted here for you to see. And our idea is try to manipulate these low-speed streaks using deep reinforcement learning. So in this specific case, we are not going to use the same blowing and suction techniques that we've been using, but rather we're going to try to use streamwise traveling waves, which were, let's say, designed and conceived by Quadrio et altri from the Polytechnic of Milan. So in this specific case, we're going to go back to single agent reinforcement learning, and I'm going to explain in a moment why. But for the time being, what is important is that we are taking as observation in this case, the streamwise component of the velocity at a given plane as we did before. And in this specific case, our control is going to be the frequency of the streamwise traveling wave. So you can see that in this specific case, even though we are considering the entire domain, we still have a single, let's say, parameter that we need to tune using our reinforcement learning, even though it's time varying. So we don't need to resort to multi-agent reinforcement learning, because in the end, our, let's say, by imposing the functional structure of the control, then we are essentially applying this control in a global sense, in a global way into the entire domain. Here, the reward is calculated as the ratio of the streamwise and total turbulent kinetic energy in the region close to the wall. So what we're going to do is that we're going to integrate the streamwise fluctuation to get the turbulent kinetic energy in the streamwise direction. And then we want to increase its relative importance with respect to the global turbulent kinetic energy, which is considering all the components. The idea behind this is that, so let's say, by applying deep reinforcement learning here, what we get is that we are actually able to increase the energy in the streamwise direction from 33% in the uncontrolled case to 42% in the control case. And you can see from this screenshot how there is a clear topological difference of the structures in these two cases. And the idea, the rationale behind this is that by enhancing this structure and by making them more energetic, we are trying to reduce and minimize the sinusoidal instabilities. So in this way, we are trying to impact the wall regeneration cycle. So that trying to avoid that this structure transition to new one and generate over and over new turbulence, essentially. This is, of course, related also to drag reduction, because if we are able to inhibit the turbulent cycles, then we are probably reducing the amount of turbulence that we have in our simulation. In particular, we have that these streamwise traveling waves can provide up to 45% drag reduction. And that was something that was investigated by Quadrio and altri. And you can see here in red, and was for a very specific set of parameters. In our particular case, even though we have time varying, we only achieve 20% drag reduction. And here you can see the history on different, let's say, episodes and initial conditions. And here should be like the best value that we were able to achieve with the streamwise traveling wave with the fixed pulsation. That is something that requires a little bit more investigation. It's something that is still ongoing as research, but this shows us that in any case, we're able to manipulate different structure, using different reward functions and achieving different results. So of course, how the physics is modified by the classical streamwise traveling waves is different from the one that we are able to achieve in this case. And of course, this is something that is worth investigating, that we are currently investigating with the colleagues in City University of London. So summarizing this part, the important part is that we are able also to use other alternative control mechanisms in DRL with success and managing to achieve what we want to do. It is important and nice that we can take scientific hypothesis, and by suitably designing the reward function, we are also able to, let's say, test these hypotheses and see what are the results. And in particular, it's interesting for me that differently from other techniques like selective frequency damping, in which, for instance, we're just gonna eliminate, let's say, by using the simulation, specific frequencies in the domain, and then we can observe the effect. Now, DRL is also providing an actuation strategy, so a way which could be more or less realizable, of course, that it can gives us an idea and somehow a way to, let's say, perform this control in first place. Of course, nothing comes for free. There is also the problem that there is a problem of controllability, in the sense that not necessarily the actuation strategy that we have at our disposal will be able to provide some sort of control in the reward function that we want. At the same time, there is also a reproducibility problem, because it's related to the fact that DRL is, let's say, trial and error procedure, and the interaction with the nonlinear problem is gonna, in general, make quite difficult to, let's say, reproduce the same results one-to-one. But overall, in general, DRL can be regarded as an effective tool for scientific discovery. The last part of this talk is something that I tried to maybe somehow tantalize you as mostly mathematical people, because unfortunately I'm not. So here, just coming back to deep reinforcement learning, we have seen that different ways of learning deep reinforcement learning is that we can either evaluate value-based methods or policy-based methods. And in particular, I want to focus here for a moment on value-based methods. And in particular, this is the definition. And here, as we mentioned at the beginning, this is the expected return over a trajectory, provided that we start from a given state and then we follow a certain policy value. Now, for each state of them, we are able to write the Bellman equation, which is some sort of consistency equation for deep reinforcement learning and for the value function. And the nice thing of this equation is that it provides us a sort of unbiased estimator for what is the return at the given time step. And by using this information, we can design an error, which is what is called a temporal difference error. And here you can see that by using this information and this estimator based on the Bellman equation, if we are able to reduce to zero the temporal difference error, then our estimation of the value is going to approach the correct convergence, the correct value. Now, typically, as we mentioned before, for neural networks in general, it's very difficult to, let's say, what motivates the use of neural network is the fact that it's very expensive to estimate the value at all these states. So what we do is that we provide some sort of function approximation. By using the TD error that we saw before, we can guide the optimization of the parameters using, let's say, an iterative method as the one that we see here. And these U here in particular represent the update that we're going to consider. And one alternative is a gradient method, which is convergent in general, albeit quite slow, and which can be partially problematic. Or alternative, there is something that is very specific for reinforcement learning, which is what we call a temporal difference learning, which is in which the update is written here, which is fast, but unfortunately doesn't come with any, let's say, convergence guarantee. So what is important here is that essentially, if you look at compare the GD update and the TD update, you see that the first term is the same for both of them, and the second one is not. So essentially, TD is faster, but it's not a proper gradient method, essentially. So despite its possible divergence, temporal difference is actually a cornerstone of modern DRL algorithms, and DDPG, for instance, that we used in the case of drug reduction, actually base its value estimation on these temporal difference error. And understanding how this works and why it works is actually a relatively fundamental research topic that is not touched upon whenever we are looking at applications. So in this postdoc that I'm doing at the moment, what we have been looking at is trying to simplify things as much as possible and looking at a linear function approximation for our value. And in this, under this assumption, we are able to write the update rule that we saw before in this form, where eta is the gradient, is the learning rate, of course, and h is the Hessian. And in particular, it's worth noting that for gradient update, H will be symmetric, whereas TD update will not, in general, provide a Hessian matrix that is symmetric. So starting from this observation, we try to have a look at why temporal difference learning is fast. So we start from a 2D example. 2D example here, we have just a very simple matrix, 2 by 2 with, let's say, a symmetric component and a skew symmetric component. And for R equals 0, we just have a gradient update. You can see here that we choose A and C to be very different, in particular because reinforcement learning is an extremely ill-conditioned problem in general. So we want to try to mimic this situation. And whenever we are increasing the absolute value of R, we see that we have in different regimes, because depending on its value, the determinant of this matrix is going to change. So in this case, it's going to be two different eigenvalues, but and both real. In this case, we're going to have only one. In this case, let's say they're going to be complex. But in all the cases that we are investigating, which are all the lines except for the blue one, we can see that by adding a sort of rotation, a sort of degree of rotation in a sense, is going to provide an increase of the convergence rate of the algorithm. So again, once we have developed the intuition on a 2D level, now we want to try to generalize the problem on an ND and try to understand why in practice a TD is faster. So now we consider an Hessian, which is built by two parts. First one is A, which is a symmetric part, and the second one is B, which is instead a skew symmetric part, and R is our parameters. Now, what we're going to do is that we're going to have a look at the eigenspectra of these positive symmetric matrices under skew symmetric perturbation. And what happens in different dimension, what we see is that the distance between the largest and the smallest eigenvalue, by introducing a certain degree of rotation, reduces quite fast and quite a lot, both in a few number of dimensions and in n dimension. So this is something that, of course, is very interesting, because what is in practice happening by adding this rotation is that we are effectively reducing the condition number of the matrix, thus enhancing the convergence rate. So guided by this intuition, what we tried was to try to unify these two updates. And the idea was to try to develop a method that would provide us the same convergence guarantee of gradient descent and the convergence rate of TD. So we developed this update, which combines both. And we tested it on two different problems. The first one is called Baird counterexample, which is a test in which typically TD was proven to diverge. So you can see here that the loss is diverging, and the trajectory of the weight in the weight space is moving outwards. And also in a grid world, which is another relatively simple problem, but larger dimensional, in which we are discovering that this estimation is performing better in our case and is converging faster for the same learning rate. Now, this was mostly to show essentially that in reinforcement learning, there is actually a lot of things that are not fully understood, and there are the work in practice that could be very interesting to explore and investigate much more from a theoretical perspective. Now, to sum up the conclusion, I know I am already like 5 minutes late, so I'm just wrap it up quickly. The takeaway message for today are that we can design drug reduction policies using multi-agent deep reinforcement learning that have performed better than existing baseline, and these that have a profound effect on the flow. We can design different rewards to target different mechanical physical processes, and based on these, we can learn suitable policies to manipulate these different physical processes and try to get some insight on them. And then finally, despite this empirical success that we are able to provide, there are still many real theoretical aspects that would be very interesting to investigate, and we have barely started scratching the surface with these TD difference problem. So, and with this, I thank you, and I leave you here the GitHub link for the first work, which is the one that had much more implementation burden, and I'm open for any kind of question. Thank you.
Thank you for your nice talk, Luca. Have you any questions, curiosities? Also from online? Okay, I have a couple of questions, more curiosities. The first one regards the second part of your talk. I don't remember the slide. Maybe the number of the slide 75, maybe. Try to go. Okay, 72. I don't remember. It was the intro of the second part.
This one, maybe.
No, the 68, maybe. Where you explained the general methodology. Here, okay, here. Okay. Can you explain how did you choose the value of y plus where you have computed the integrals? Why y plus less than 60?
So it's in general, we wanted to try to include as much as possible what was the let's say the cycle, the regeneration cycle, and trying to leave out, let's say, outer movement that were not affecting the problem, that would have made things let's say less evident, because of course the more you integrate, the less you see, because of course the fluctuations and let's say you're integrating over a larger domain and it's more difficult. In general, it was mostly let's say it was not necessarily principled, but overall that was more or less from the literature where you could see the effect of the control in practice, and then relating to that we decided to go for y plus 60. But to be fair, we didn't necessarily explore the sensitivity with respect to this parameter.
Oh, okay, it could be interesting, I think, because maybe the rate of convergence could be affected by how you choose this quantity, maybe, but I'm not sure about that.
I mean, one interesting thing is that by, let's say, to check these, we, so to speak, just need to change the value of the limits of the integration. And it's, let's say, the nice thing of this is that it's very open to experimentation and see how the different parameters are affecting the, let's say, the overall outcome in a sense, and trying to make a sense out of it afterwards. That's the most important thing.
Okay, thank you. So I have another curiosity. I'm not an expert of reinforcement learning, and I have understood that all the methodology is affected by a process of trials and errors. Okay. Are there stabilization strategies to accelerate the order of convergence and to be sure that you are converging toward the right state?
So in general, not really. So the problem is that oftentimes you have not available the solution. So what you get is typical, like it's difficult to get in a sense an estimate of the convergence rate because you don't know the target. And of course, you have the problem that you might be, especially if you're using neural network, there are different parameter, let's say, settings that are equivalent with respect to the loss that you are looking at, which means that all these are kind of minima that are all at the same level, but there is no specific way to make sure that this is a global minima or a local minima. Is not even sure what does the let's say the parameter space looks like if it actually has a global minima. And what is used in reinforcement learning is exploration actually to try to not get stuck in these local minima. But in general, it's very difficult to let's say accelerate convergence to a certain extent. Although I must say that I'm not, I only know that typically it's very difficult to make estimates in this direction. There are only a few cases in which you can estimate let's say also the convergence rate in a sense in reinforcement learning. So it's definitely something that would be worth looking into.
Okay, thank you for the clarification. Okay, there are maybe Niccolò, have you a question? Okay, yes, you can.
Yeah. Thanks. So, well, first off, thanks for the presentation. Can you hear me all right?
Yep.
Okay, great. So yeah, once again, nice presentation, very, very interesting. I have a couple of questions. Like first off, in terms of, let's say, the data set, or let's say like in the channel flow, is just a curiosity because I just use blowing and sanction basically to trigger transition and those kind of things. Does it affect let's say the grid convergence properties? Like if you are playing around with suction and blowing, changing the fact that you are actually dealing with a DNS? Are you using the same, by the way, like, are you using the same resolution of the classical DNS of Reynolds Tau 180, or you're playing around with that?
No, so in general, the resolution is the same, which is, although it's slightly coarse, if you wish. So a proper DNS might be slightly, if you want to do it, we are on the verge of being slightly under-resolved, but higher resolution will be a bit problematic for the actual time that it takes to run the entire thing. But in general, we followed the resolution. It's the same as like the minimal channel from Jimenez. So that's kind of how we sized the simulation. The same time, one interesting things that you brought up is like the stability is more about, for me, it was mostly about time, because what we had to do is that we had to reduce a lot the actual time step of the simulation, because whenever you are changing the boundary conditions, you are imposing a velocity that can change quite a lot, quite significantly, and you're doing it where the simulation is as the smallest cells, which means that the CFL number is heavily impacted by
Of course.
by that. So which means that we had to reduce quite a lot the time step in order to make sure that, let's say, the computation was stable from the computational perspective in that direction, but from the in terms of spatial discretization, we kept the same in all the cases.
Okay.
Using
And since you mentioned, yeah,
sorry, just to finish, using an open channel helps in a sense because then let's say essentially you have at least for the solver, it's let's say if you do the calculation, you don't have the same requirement in Y.
Yeah, of course. That's reasonable.
One wall, essentially, not two.
Since you were mentioning like in terms of stability, okay, well, maybe I saw like the hands by Federica, will try to cut it short. You learn a policy, let's say in the small channel flow, and then you apply it to the larger one, or in general, like you learn a policy and then you apply it. First, a couple of things, like in terms, is it stable? I mean, did you consider, like, did you integrate for very long time integration? These policies, they are stable. And secondly, if these affect, like, statistically convergence of the case, like if you consider long time integration, all the statistics do converge to a certain state.
So in general, not, let's say, you can see a variation of, as here I pulled up the plot, but essentially what you get, this integration was for T plus 1,500. So in general, and then we have run also, I think 3,000, I think at a certain point. But so in general, the simulation is stable, although you have periodic oscillations. So the value at which you are stabilized, except you exclude the initial transition, then you maintain sort of, let's say, I wouldn't say it's exactly the same all the time, because I haven't really looked at the individual fields over a very long time. I've just looked at the statistics, and for the statistical perspective, you see oscillations that are comparable with what you get for the opposition control. Sometimes it goes a little bit down, sometimes it goes a little bit up, but more or less is somewhat stable, let's say.
I mean, stability is more important than having like a statistical convergence. At least that it's stable, like it's more relevant.
No. From the numerical,
anyway,
it stays where it is, to the extent that we have looked at. Let's say,
of course.
I didn't really run extremely long simulation in this case, so I'm not able to tell from that perspective.
Okay, yeah, thank you very much for the answers.
So yeah, thanks a lot for the very nice and interesting talk. I have actually one curiosity about the last part. So when you were talking about the TD method, so which is I guess it's connected with the let's say more standard Hamilton-Jacobi-Bellman equation for the value function. Let's say I've also seen that in that kind of context. So in your case, you define that with a single, let's say the only influence is if I got it right, is only one temporal step, like t plus 1 and t. So like given like the importance that you said about the kind of interesting approaches that they could have also in the scientific discovery or use, does it so is it interesting to also have memories inside that, so like having a window to look at it?
So there are two elements here. So of course, let's say in this specific case, we had look at what is it called a TD error, TD learning. But to be fair, to be complete, and the name is TD0 because we are only using one step.
Okay.
However, there is also a TD lambda method, which is instead like spanning multiple time steps. The thing is that, of course, is that it requires more memory to store like a longer trajectory of the states in order to compute. But let's say the biggest problem or the biggest limitation maybe is the fact that we are always in reinforcement learning modeling the environment as or the problem as a Markov decision process. So suppose
you forgot.
supposedly there is no memory in the method. Now, this is of course a very crude approximation, and we know it's most likely not true if you're considering a turbulent flow, or in general, if you're not we think in terms of Moritz-Zwanzig formalism.
Exactly.
Whenever we are not observing the full state, then it's very likely that you're going to introduce some form of memory and or history effect because simply things are happening outside of the let's say of the manifold which we are exploring let's say, or observing more than exploring.
Exactly.
But so in principle, there are these two conflicting elements. So on one way, you're modeling everything as a Markov process, which are like a bit butchering the problem, but at the same, which is very engineering like. But at the same time, you have most likely history effects or probably history effects that can affect the entire evolution of the individual observables that you're tackling.
I see. Thanks a lot.
Any other questions? Okay, let's thank again Luca.
Thank you very much for inviting me. It was very nice to share a little bit the results, and yeah, looking forward to see at least some of you in some conference, possibly.